I'm honored to be here and to be talking to you. And I would like to be able to say something about Abdus Salam in the starting. And I have the particular obligation to do so because I was at ICTP in Trieste for almost half of the time over a period of 10 years, from the very first day when you opened in Piazza Oberdan until 10 years later. I was there a good proportion of each year. Unfortunately, I never had the pleasure of a close collaboration with Professor Salam, so all I can do is to dedicate this presentation to him. Apologize for not being able to do any more than that. I'm particularly anxious to have your reaction. You will immediately notice when you ask a question or make an objection that I have a handicap here. And our chairman has kindly agreed to help translate or repeat for me the question that you have, and I hope that this will not keep you from asking questions and objections. Criticism is very hard to get. So I will be very grateful for anything like that. Okay, so let's go. Here is a quick summary of what I want to talk about. I noticed that the colors were lost, so you can see what it was that I wanted to emphasize. But this line here contains the highlight of the talk. The new thing I have to tell you about, which I think is important enough for me to come this long way to tell you about, is what comes in here. The main application will become later here in astrophysics, and there are many other applications what I'm talking about. Okay. So first I want to try to convince you or say something about why I think that our action principles are very important. First of all, you can go back in history, and maybe you have read the story of Maupertuis and what the discovery of the first action principle did to him. He fell for it simply because of the sheer beauty. He fell a little too hard. He took a religious interpretation of it, and that was not popular at his period in history, so he had tremendous difficulties because of that. His position in Berlin was eventually taken by Lagrange. Both Lagrange and Einstein share something about their attitude to variational principle. You may not remember, but the motivation of Lagrange's work, where he discovered the Lagrangian and all the technology, was to avoid having to do what Coriolis had to do to transfer, to make coordinate transformations in complicated systems. In fact, the way we teach Coriolis forces in the college nowadays, I think you will agree, is Lagrangian methods, because any other method is too complicated. So that is one motivation. Then there is the statement of Poincaré, which I will quote a little bit later, which says that basically that a variational principle, an action principle, joins together the various equations that describe the system in a very tight system that gives you the feeling that the thing is natural. I'll get back to that. And I'd like to add for myself that I think that today the greatest advantage of variational principles is the tremendous power of prediction that they have, which is not shared by other systems. Now, early history of variational principles, we have to quote Gibbs as the most important milestone. What he did was postulate a principle of minimal energy, and from this principle of minimal energy, he deduced the two main axioms of thermodynamics. However, the odd thing is that, as far as I know at least, he never wrote down the action, the energy functional. I've been reading his papers and I have certainly not found anything that suggests that he used a formula like that. But this formula has the property that if you keep S and P fixed at vary V and T, then it has a stationary value at precisely at the surface on which we define by these two equations. His approach was the geometric. He starts with he thinks of a four-dimensional space with the four variables V, T, S, P, and then he considers these two equations that he gets by minimizing the energy, and that defines a two-dimensional surface in the four-dimensional space. So it's a nice geometrical picture, and it so impressed Maxwell that he prepared a statue, reduced unfortunately from 4 to 3 dimensions, of the substance of water. And there is a statue. It was built or commissioned by Maxwell and shipped as a present to Gibbs. Maxwell became a great exponent of Gibbs' work in Europe, and he did a lot to make it known. Towards the end of his life, Maxwell also was very interested in trying to make variational principles for thermodynamics, but he died too soon. Now, once we have the Gibbsian minimal energy principle, the first thing we need to do is to get an energy functional, and I showed you one that does exactly that. And then we have to localize it, because we are not really interested in systems that are homogeneous, but systems that vary from one point to another, extended system. And the irony of it is that that's exactly what the title of Gibbs' paper was about heterogeneous systems. However, something I was not grateful to Gibbs for, and that is the choice of variables that he used. He used the variable V, and then he used fractions, molar fractions. These variables are completely unsuitable to doing continuous hydrodynamics or thermodynamics. I'll give you one example to demonstrate that. This formula shows how to add together the free energies of two gases when you put them together in the same vessel. F1 and F2 are the free energies of a certain amount of gas 1, and F2, the free energy of the second gas. N1 and N2 are the molar fractions, and we put the two together, the free energy is given by this formula. But if instead of using the free energy of a certain sort of quantity of gas, you use the densities, this tremendous formula simplifies just to that. The same thing happens with entropy. If you express yourself in terms of densities, there's no such thing as a free energy of mixing. There's no such thing as an entropy of mixing. So you can imagine that everything you do is tremendously complicated by simply changing variables. I've tried to talk to chemists about this, and I had a strange experience to discover I couldn't even convince them what those densities were. It was so far from their way of thinking about things that when I talk about densities in plural, they were unable to follow me. So therefore, things that I tell you about, but I will avoid details, of course, about thermodynamics will have a somewhat unusual flavor to it, maybe. Okay, so once you find the energy functional, then you have to localize it, as I say. And when you've gone through these two stages, of which the second is a little difficult, you end up with this. This is the energy functional of a continuous system extending over the interior of a certain vessel. The density is rho. It's taking the place of the volume. F is the free energy density. S is the entropy density. T and P are temperature and pressure. And V is the velocity. By the way, the relations that take the place of these ones in the continuum domain. I haven't written them down, but they are exactly the ones recommended by Callan, who is credited with the greatest insight in how to go from the finite to the continuous systems. Everything that comes out is completely standard. Language is different, but the result is the same. We still have to pass from minimum energy to action principle. That will come a little later. Now, why do we want to have action principles today? Well, I already said so. If you compare QED and the standard model and its predictions with what happens in the other sciences, you will be struck by the fact that the other sciences essentially don't make predictions. They describe, they account for, they explain, but they don't make much predictions. Finally, there's the question of avoiding errors. I will tell you here about an error that I made myself. I don't want to talk about the errors of other people. Namely, there was a case where I had something which I thought of as a Hamiltonian, and I thought I would use it to derive a virial theorem. Well, you can derive virial theorems, but what I had forgotten was the fact that if the Hamiltonian you have to use must have this property. If it doesn't have this property, no matter how physical it is, no matter how much you think it represents energy, if it doesn't have this property, it's not capable of giving you any result like a virial theorem. Here are two other examples. People who do Navier-Stokes equations together with the Fourier approach and so on, very frequently, if not always, introduce an expression they call the energy. But giving it the name of energy does not give it the properties, that it does not give you the right to deduce any particular properties. The same thing happened in, let me see, maybe that comes later. Okay. Oh yes, here we are. The Euler-Lagrange equations of an action principle have a tight structure. This is what Poincaré had in mind. This is what he said somewhere. And I think that's to be interpreted as a strong endorsement of variational principle. I think that's what he had in mind. But there's something I wanted to add to this, which somehow has gotten lost. In development of astrophysics from Eddington forward, there is often the question of getting properties of model stars without actually doing the integration of the differential equations. And this has been taken over by textbook writers later on. And I'll give you what I think is the worst example of a misdeed here in this respect. That was a book that says at a certain point, we now define the total energy as this expression. And then they proceed to make deductions from this, is taking it for granted that what they have defined to be the energy has the properties of energy, and that you can make any deductions from that. This is very common. That's why, one of the reasons why I think we have to have a variational principle whenever we can, and a variational principle should give us a Hamiltonian, and then when we call that the energy, we know what we are talking about. Okay, action principle. The first one may have been born in 1980, but actually it may go back to, possibly go back to about 1738 in the work of Bernoulli. Now this is found in a book by Vetter and Walecka, published in 1980, and this action contains two variables. It contains the density, it contains a velocity potential, and the velocity, as you see, is a negative gradient of phi. So the variables are v, are phi and rho. This is, of course, the kinetic energy this would be some potential, like the gravitational potential, and this is a potential which, in the case of a polytropic system, would be some power of rho, but it can be many other things too. Now, if you vary this action with respect to rho and to phi, then this is what you get. The coefficient of delta phi is the quantity which has to be zero by the equation of continuity. And the thing that multiplies delta rho is, in fact, the Bernoulli, the integrated Bernoulli equation. Or rather, the vanishing of that thing is the integrated Bernoulli equation. Those two equations are the basic equation, or in fact, the complete set of equations of elementary hydrodynamics. So this has been available since 1980, and people do not use it, although Vetter used it prominently in a recent review that he wrote. It's very what is the word? It is not used, in other words. Okay. Now there are two limitations to this. The first limitation is that the flow is limited to be potential flow. The velocity has to be a gradient. And this is a very strong limitation, and that perhaps is enough to explain why this particular action principle has not been used. People use the equations, but they don't use the action principle because it has a very limited application. Another thing that limits it is the fact that there is no temperature there. So it does not include thermodynamics. Now you can move up to thermodynamics. I will show you in a moment, and then you can, once you have the thermodynamic formulation, you can eliminate the temperature by using the adiabatic condition. So you can always get back to this stage. But when you're doing that, you're in fact making a projection by using one of the equations of motion. So in fact, what you're doing when you pass from thermodynamics to hydrodynamics, you're going partially on shell. And as Professor Ferrara knows extremely well, that if you want to generalize something, such as supergravity or whatever you're working on, the first thing you must make sure is that you don't have any constraints. You must have a constraintless formalism. Then you can work with it. Then you can add theories together, make one interact with the other. But you cannot take a theory which is described by a constraint formalism and make it interact with something. It just doesn't work. And I will show you how this statement applies to thermodynamics. So it's limited in these two ways. So we have to move up to thermodynamics, and here it is. Now this quantity St minus P is, you might recognize as being a local version of the energy functional of Gibbs. If you vary this Lagrangian with respect to T or to density, then you will get the equations of thermodynamics coming back again. And in particular, if you vary T, if you vary the temperature, you get an equation involving the temperature, and you can use that to eliminate the temperature from the equations. That is the projection. That's the on-shell projection that takes you from thermodynamics to hydrodynamics. Okay, now we come to what I would like to believe to be the highlight of this presentation. I'm going to show you an action principle for hydrodynamics and thermodynamics that overcomes the other objection. Namely, it's going to be applicable to arbitrary general flows. I've been working on this for about 5 years, and everything else I've been working on has been suffering because I'm obsessed by this idea of getting a variational principle for general flows. It was found at first by a very minute study of the Navier-Stokes equation. The Navier-Stokes equation has much greater range. It allows all kinds of flows, and it's very successful in some particular application. For example, it's very successful in studying certain kinds of flow in cylindrical Couette flow that I will come to a little bit later. So that's how I found it at first. But I will show you another derivation which I like better. It's somewhat more elegant. The challenge is to find an action principle with exactly 4 degrees of freedom, because classical hydrodynamics has 4 degrees of freedom. Now, the problem is that we already have 2 of them. Why do I say that? I say that because I'm not willing to give up the equation of continuity. I think the equation of continuity is a centerpiece of hydrodynamics, and we cannot afford to give it up. That means that the idea of a velocity potential cannot be given up, because the velocity potential is the canonical dual to the density. So we have one canonical pair of variables that we cannot do and we cannot sacrifice. So we only need 2 more. Okay? And this is what's going to make the answer to the question almost completely unique. We need to find more velocity variables, but we cannot give up the fact that we already have one velocity potential and 1 density. So how to do that? Well, the question of counting the number of degrees of freedom is much easier in a relativistic theory than in a non-relativistic theory. At least it's much easier for me with my background. And so I will present the solution by going first to the relativistic domain. Well, I should first say that this type of variable is strongly indicated because if you want first-order differential equations for the velocity, then the basic variables has to be a potential. So we have already a velocity potential whose gradient is the velocity, and here we have a vector potential whose time derivative is the velocity. This is the natural way to go. The problem is that this has too many components, right? This thing here has 6 degrees of freedom if you make x itself the variable. So far too many. So what to do? So we go to the relativistic theory. Now we want to have exactly 2 propagating modes, 2 pairs of canonically conjugate variables. We already have one, the scalar field for potential flow, and now we need 1 more. And the only other field is available, other than scalar field, that has a single spinless degree of freedom is the Notov. This is a theory invented in 1964 by Ogieretsky and Polybarimov. It has appeared in string theory later on as the Karl-Bramont field. And it has appeared in the study of vortices, of vorticity, by Lund and Regge back in the 60s. So that's what I'm going to show. But now first we have to make these first theory relativistic. And so this is the relativistic version of the Petter-Wawrinska theory. Here you see the density is there, and here you have another scalar field, which is the velocity potential. And in this theory, you have to expand this way, and then you expand the whole thing in powers 1 over c squared, and the result of that is the Petter-Wawrinska Lagrangian. So this is not difficult. So this is the relativistic version of the potential flow theory. Okay, so now we go to the next one. The field in this theory is a relativistic 2-tensor, antisymmetric, a 2-form, and the theory is a gauge theory. This is what makes it difficult to understand it directly in a non-relativistic theory. I will show you, but you probably could not have guessed it. It's invariant. The theory is invariant of gauge transformations, where you add an exact 2-form to y. C is an arbitrary 1 form. The gauge invariant terms in the action are 3. As the main kinetic term, which contains the square of the 3-form dy multiplied by rho. We are not in empty space here. Then there is this term here, which is an interaction between, these are the two forms, so this is the fourth form altogether. And here you have the 2-form y, and this one here is Maxwell field strength. And so this is not an interaction, but a mixing between this field and Maxwell's field. And as people in string theory know very well, this mixing gives the photon a mass. You can make this match as small as you want, and this is an added interest and attraction of this theory, but this is not what I'm going to talk about. So from now on, I will not mention the electromagnetic field. Then there is this term, the only other term I think you can add, which is gauge invariant, which has to remain a little mysterious because it's there only because it exists, not because we wanted to accomplish something. So what it will mean, we're going to have to find out later. So this is what I call a minimum extension of hydrodynamics from potential flows to general flows, and I would say that it is pretty near unique. I have insisted on maintaining the equation of continuity, although other than that, I not impose any constraint. Now, to get down to the three-dimensional description, so we can recognize what we are dealing with, we choose a gauge. We choose a gauge in which these components are 0, and this is a little misspelled. What I mean here is this condition here. Look, what I call xi is a 3-vector field, and it's related to the space component of y. And okay, I got a little confused right now, but I'll tell you that you can fix the gauge, and you can fix the gauge, and then you're going to have 2 constraints. This constraint is very important, and this one here is important also, but I haven't discovered any particular case where it plays a major role, but I will show you what happens because of this constraint. Now, Galilei transformations. Now here's an interesting question. You already have a velocity that transforms under Galilei transformations because the Fetter-Lorentz Lagrangian is invariant of the Galilei transformation. And now you introduce another vector field, and what does that do under Galilei transformation? Well, the answer is that the Galilei transformation is a limit or approximation to a Lorentz transformation. But the Lorentz transformation takes you out of, changes the gauge. So a Lorentz transformation has to be supplemented by a gauge transformation, just as you do in electrodynamics. And the total result of this is that the field X is inert. It does not transform under Galilei transformation. More precisely, each component. Oh, thank you very much. More precisely, each component of the field X transforms like a scalar field under Galilei transformation. Now there is a new action. So the new action is the Fetter-Lorentz, or rather Lagrangian. You see you have the phi dot and this term here, which is the essential parts of the Fetter-Lorentz Lagrangian. And then there is a new term, which is the non-relativistic way of writing dy squared. This is the gauge invariant kinetic term reduced to a particular gauge. And it's a 3-dimensional field. And then you have the usual thing as before. Now let's list all the equations of motion, all of the other Lagrange equations, to see what this theory means. first variation of T, but I've already eliminated the T, so we can talk about that here. Variation of phi gives you a continuity equation, and then from this equation you recognize that the quantity inside the bracket, inside the parentheses, is what you must identify as flow. So we know now that one particular combination of the two vector fields is interpreted as mass flow. We don't know the interpretation of the other one yet. And this is a velocity that appears in the Navier-Stokes equation. From the equations of this theory, you can try to eliminate one of the velocities and so that you remain only with this velocity. You can do that, but then you get Navier-Stokes. Almost in certain important applications, not always, but in certain important applications you get practically exactly Navier-Stokes. And this, in fact, is how I found this Lagrangian in the first place, by working on Navier-Stokes. Okay, so that's the, here's the third differential equation. If you let me take this other combination of the two velocity fields and call it M, then this can be identified with what's called momentum in 10 minutes. This is a pity. I think I will ask for another 5 minutes since we have had a cancellation. Can we do that? But obviously I have to go faster. This also appears in the work of Lund and Regge on vorticity, and it's from them that I understood that this M is actually what's called the momentum in non-equilibrium thermodynamics. And so the new item is that the momentum is not the same as the mass transport. Variation of the density gives you this equation, and I won't say anything more about it, but if you take the gradient of that, you get something that is very, very well compared to Navier-Stokes. Viscosity. Of course, we are talking about variational principle. We don't have viscosity. However, we are in exactly the same position as the so-called non-equilibrium thermodynamics, which begins by writing down all possible conservation laws, and then they add in the viscosity term by hand. We'll do exactly the same. So the only difference is that the conservation laws that we are using here come from an action principle, and the Hamiltonian is a constant of the motion. The attitude to viscosity is not changed. It's the same as it's always been. Application. Cylindrical wet flow. This is one that I used in order for my initial studies of this problem. It is a flow between two concentric cylinders. You can rotate the inner cylinder and you can rotate the outer cylinders, and you get some kind of flow which at low speeds is laminar. And the problem of greatest interest is to predict at the point at which turbulence sets in. The onset of turbulence, that's a big deal here. Here is looking down at the stream. And this picture is a picture that shows the onset of turbulence. The coordinates are the speed of rotation of the inside and speed of rotation of the outside, respectively. And below this line, you get laminar flow, and above it, you get all kinds of things happening. Now we can ask this question from this new action principle that I'm showing you, and it predicts a line that looks very much like it. I have not pursued this. I'm not an expert on breakdown of turbulence, but I have the impression that it does much better than anybody using Navier-Stokes does. Many things that need to be done. Now we come to the main application. Okay, here I'm going to take have to go more slowly. The sources for Einstein's equation. Now, this formula is the formula proposed by Tolman in 1934 and has been used by everybody almost ever since. I'm not going to use it. I would like to look at the problem of putting a source into Einstein's equation. It's the problem of coupling two different theories together. One is Einstein's theory of free gravity. The other is some kind of material, mechanical, or fluid type of theory. And to have two given theories, and the problem is to join them together to make an interaction between them. Okay? That's not what's happening here. This is pure phenomenology. We don't know. It's true that the energy momentum tensor on the y has some similarity with what you expect for a stream of particles. Has nothing to do with fluids, by the way. But with streams of particles, yes, it has some similarity. But what are the properties of that theory are completely unknown. And the only thing that is sure is that the Bianchi identity will impose some conditions on T. And that's the only input you give, that the theory gives, about the matter sector. Only that it has to fit into the scheme with the Bianchi identity. This is a point of view which is possible. It has been defended by many people. It continues to be used. And the verdict I make is that it's too easy. It's just too easy. You can certainly do that, but you will never be able to predict anything by doing that. I make my statement strong because I want them to be heard, okay? I hope you forgive me for speaking my mind. I have only a few minutes. Okay. There also it violates the continuity equation. And I don't see how you can generalize hydrodynamics and giving up the continuity equation. I just don't see how you can defend that. Okay, so why not using the action principle? Because up until yesterday, we didn't have an action principle that was useful. Well, since about 1980, we had Feta-Wawrinska, which we could have used, and we would have created this theory here. The action is the Einstein action plus the action of the relativistic form of the Feta-Wawrinska theory. And today, because we have this new theory with two velocities, we can add in the Notov field. And now we have, for the first time, a source for the Einstein equation, a source expression for the right-hand side, which satisfies the Bianchi identities, satisfies continuity equation, and which allows for rotations. This is the great news that I'm offering here. Did you know that there's a virial theorem for fluids? It's actually very interesting. The virial is not x dot p, but rho times phi. And with this, you can get an exact virial theorem for any one of these theories. And when you calculate the commutator of D with Hamiltonian, which is the same as the time derivative of age, then there is this wonderful surprise here that these two things, these two parts of the kinetic energy come in with opposite sign. Now that's extremely interesting. If you think about it, it might have some very strange applications. And in fact, I don't have time to tell you about that. Now, here is one more application that I want to spend a few minutes to talk to you about. And in 1904, a man called Wilson did some experiments. He took a cylinder, thick cylinder, placed it vertically and made it rotate. Then he put a magnetic field along the axis, homogeneous magnetic field. Okay, so the thing is spinning, magnetic field is on it, and he goes in there and he puts an electrical wire, a measuring device across the thickness of the cylinder. Okay, he measures this electric field. He publishes that. It is read by Einstein. Einstein and Laub wrote a paper that they analyzed this experiment and claiming that the thing proved the transformation was a proof of transformation properties of special relativity. Well, it did not prove anything of the kind because what they were able to do was deal with linear velocities only. Lorentz transformations involve only linear velocities, no acceleration. It's a rare example where Einstein made a very big mistake because he actually did insist 2 times in the paper that his calculation is valid. It took until 1995 before somebody had the courage, and the journal had the courage to accept a refutation of this analysis by Einstein and Laub. It was done by Pellegrini and Swift in 1995 in the American Journal of Physics. And they showed the complete inapplicability of the reasoning of Einstein and Laub to this event. So now 20 years more have passed, and during these 20 years there's a debate. There's now 15 and 20 or 20 papers on the subject, and people still do not know how to analyze that experiment. And what does it tell you? It tells you we up to now we do not have a theory of electromagnetism of extended body if they're allowed to rotate. Only if they're allowed to move with constant velocity. Otherwise, we simply do not have a theory. Except I'll give you one now. Because, you see, when this thing is rotating, especially if it's a metal one, you're going to have a rotation of the ions, of the iron, or you're going to have the rotation of the electrons. And you're going to have two independent velocities of rotation. So we can apply our theory. The theory has a conserved current, of course, including the electromagnetic field does not change that. The current is still conserved. And then you write down the Bernoulli equation, and it takes this form. Well, we don't have to go any further than that. This is actually enough. This is exactly the equation that answers the experiment. It's the equation obtained by Einstein and Laub, but it has nothing to do with Lorentz transformation whatsoever. And the factor that comes here is the one that was measured by Wilson and later by other people. And you see quite clearly that this is a parameter that is model dependent. It has nothing to do with the Lorentz transformation. It is model dependent. You cannot predict that. You can measure it, but you cannot predict it. This is a kind of a scandal, in my opinion. So I've talked about these 3 applications. Now, if I still have a couple of minutes, I'd like to talk about mixtures. Now, when it comes to mixtures, for example, 2 gases, 2 fluids together, then I cannot offer you the same unique theory as I can do for a single pure fluid. So for example, I do not know yet exactly what to do with superfluid helium, or for that matter, for any other mixtures, except when the flow is potential. Okay? So now, from now on, in the last few minutes, I will limit myself to potential flow. Then, the thermodynamics that I showed you before has wonderful applications to mixtures. So here is the Vetter-Walensky theory again, and now with a full thermodynamic application. Now we can deal with mixtures. Now, I will only give you a hint of what's going on here. The Lagrangian is now in the first approximation. It's natural to assume that the Lagrangians are additive. If there is no interaction between the 2 species, then you get the actual total action by just adding the individual actions. So here you have the free energy of the first liquid, first fluid, and of the second fluid. You just add them together. And then this is a very pregnant type of expression. I've just added the entropy term for the two theories together. And then, of course, this quantity in the parentheses is a formula for the entropy of the mixture. Now, entropies of mixtures is a very vital field. And this is actually amounts to a model for the entropy of the mixture. I could not find anybody anywhere that has a mathematical model for the entropy of mixtures. So if this is successful, it's something very new. But mostly people will refer to tables for information of this type. Now the adiabatic condition of this is this derivative of this thing with respect to t should be 0. Shows you why you should not eliminate the t in each individual theory beforehand, because there is only one adiabatic condition. It involves both the free energies. This is F1 plus F2. Okay, so the adiabatic condition is now to be resurrected, to be investigated afresh. This is also something I don't find in any of the textbooks. Now, in this figure, I'm going to tell you that in my experience, and I've made many applications, in this formula, S1 and S2 tend to be constants. So what this formula says, is initially only a guess, is that the total entropy density is a linear function of the two mass densities, with fixed coefficients S1 and S2. Okay? But more generally, you have the question you want to ask is this. In the S1, S2 plane, which allocation of entropy between the two systems is actually taking place? Well, in many cases, it can be obtained by using Boltzmann's idea about entropy, but I have to skip. I can't go into the details. This shows the application of the theory to dissociation of hydrogen in the atmosphere of a star, first done by Saha in about 1920. Oh yes, this is something I love. So here's I'm going to abuse my privilege for a few minutes. Okay, just a few minutes. Okay. You all know about the history of astrophysics, about the so-called gas spheres introduced by Emden in 1907. He postulated a sphere of gas interacting with the interaction given by the attraction, the gravitational interaction, plus the pressure of the gas together. This theory was developed by Emden and used by Eddington, by Chandrasekhar, by many people later too. It gives you a family of model stars that are known as polytopes. The problem was that this equation that came up, this Emden equation, didn't have any solutions that were regular from the center to infinity. And so, starting with Chandrasekhar, people started making composite polytopes. Two different polytopes, one polytope outside, another one inside, and then joining together. And this never led to anything very interesting, although it's still being done, because nobody knows really what boundary conditions to put at the interface between the two polytopes. So what I decided to do was to look at a gas sphere where the gas is a van der Waals gas. But this is natural, because if you have a gas sphere, and the influence of gravitational field is going to be compressed. It's certainly going to condense, right? It's not going to be a gas all the way into the center. It's going to condense at a certain point. And by simply putting in an equation of state of a van der Waals gas, you can simply calculate it. You find out where the transition is. And the transition, by the transition, I mean the the edge of the yellow region. So this is the surface. So you have a gaseous atmosphere, and then you have a fluid or even maybe a solid in yellow interior. Okay. Now let's ask, where is the Schwarzschild radius? The Schwarzschild radius is something you measure the metric out here, and you find it's 1 minus 2m over r, and you measure the metric, you know 2m, and this 2m is what you call the Schwarzschild radius. In a planet like the Sun, the Schwarzschild radius is 5 kilometers from the center. In the Earth, it's a couple of centimeters. However, you could imagine that the Schwarzschild radius was rather much bigger. It could even be bigger than the star. Could in principle be. And now what do you think will happen if gradually the atmosphere condenses on the surface of the star? Over a long, slow period, the atmosphere condenses. Eventually there is no gas left on the outside. Well, that means that outside you have the Schwarzschild metric. And if you can find physical conditions such that in the limit, when the atmosphere is gone, that Schwarzschild radius coincides with the surface of the star, then you will have made a black hole. Right? Yes?
10 minutes.
Okay. What did you say, 1 minute?
10 minutes.
10 minutes more?
No.
Oh, the 10 minutes up. Okay. Okay, so that's my favorite model of a creation of a black hole. It becomes a black hole only at the limit when all the atmosphere is gone. Before that, it's physical. You can go inside. There's no physical region whatsoever. It's only the very limit when the atmosphere is gone that the inside becomes inaccessible. Thank you for your patience.
One question. I was interested in this question of the variation. I would like to understand exactly. There are variational pieces for the Navier-Stokes for the.
What about Navier-Stokes?
For the Euler equation, I mean, there are variations.
Yeah.
But they are very, useless because basically they increase the number of degrees of freedom, and you do not know how these additional degrees of freedom are connected with the observable. What I wanted to know is, suppose I do know at a certain instant of time the field of velocity and the field of the density of a fluid. Can I calculate your potentials? They are the.
You mean if it predicts the future as a Cauchy problem?
At one point they have this.
No. You have to know the initial values all over the place at one value of the time. Then you can predict.
At one value of the time.
Yeah.
At one value of the time.
Yes.
Is your description? Can your description be deduced from the observable?
Oh, you mean if it can be verified?
No. Whether you have.
It's not the same thing.
Did I understand? You are describing the field, the fluid, by a vector potential and by a potential, right?
Yes.
And plus a density, I suppose. Okay. These degrees of freedom, if I give you the state of a fluid at one point, can you calculate those ones?
No, because we do not yet know the right interpretation of the two velocities in any detail.
Okay,
so it's a mathematical model, but it makes definite predictions.
Okay, no, but let me just tell you why I was so interested at one point.
Yeah.
I was looking at the particular problem in oceanography, motion of very big vortices, in interaction with Rossby waves, and I thought that because these things are almost stable, you could try to analyze them, looking at it like solitons in interaction with electromagnetic, with some kind of wave field. But I needed one kind of variational principle in which you have one description at the initial time, one description at the end time, just like the variational principle for the.
I cannot offer you a complete satisfaction.
Okay.
However, I have a model with one parameter,
Yeah.
which you can try to fit to the observation.
Okay, very good. Okay.
And then the solution will be the answer to your question.
Okay, we'll discuss that.
Does that make sense?
Okay? Okay.
Can you please allow one more question?
Oh. Okay, I have a question.
Good.
In Fetter and Valeka, how do you introduce vorticity?
Exactly the same way it has been done traditionally for the last 50 years. Namely, you have a system of conservation laws, including one that's called the conservation of momentum, which I showed you. You simply take the quantity mu Laplacian V and put it on the right-hand side. That's what people have been doing for 50 years and have no improvement. That's what I have to do too. When viscosity becomes important, of course you are losing energy, and you don't have a variational principle anymore. Is that okay?
Thank you very much.
Thank you. Okay.